Today we're going to be talking about how to tie all of our previous work from the last two sections together to talk about all possible zeros of polynomials. So this can include situations where it's not easily factorable, you can't easily use U-Substitution, or where those zeros themselves are not actually real numbers. As always, feel free to jump to a particular part of this video that you want to know about, and just make sure that you're always taking really active notes and actually pausing and trying it on your own when prompted to do so during the video. The remainder theorem is actually something that you have seen before, even if you never named it. So if, for example, you just had a basic quadratic polynomial, let's say something like x squared minus 2x minus 3. And you factored this guy into x minus 3 and x plus 1 because negative 3 and positive 1 multiply to negative 3 and add to negative 2. And then you set up your two little mini equations, x minus 3 is 0, and you got 1, 0 to occur at x is equal to 3 by adding 3 to both sides. You set up another mini equation of x plus 1 could be 0, and then you got x is equal to negative 1 by subtracting 1 from both sides. So your two zeros occurred at negative 3, 0 and positive 3, 0 and negative 1, 0, indicating that you had solved for those x-intercepts. Well, if you noticed, when 3 was a 0, that meant x minus 3 in parentheses was a factor. And that's exactly what it says here, that if you have k being a 0, in that case 3, then x minus k is a factor, in that case x minus 3. For the other 0, negative 1, then the parenthesis of x minus a negative 1 became x plus 1, just as you would have noticed from the other parenthesis. Another way of reframing that is if I were to literally plug in either of these to the original equation. So for example, f of 3 would be 3 squared minus 3 times 2 minus 3, then I better get the y value of 0. So the 3 squared gives us 9, negative 2 times 3 gives us minus 6, then minus 3 is still there, 9 minus 6 gives us 3, and 3 minus 3 gives us 0. Similarly, if we plug in negative 1 all squared, minus 2 times negative 1 minus 3, negative 1 all squared gets us 1, negative 2 times negative 1 gets us positive 2, still have the minus 3, and again 3 minus 3 is 0. So the remainder theorem says literally that you just should expect that when you plug in a 0, also known as an x-intercept, you better get the result of y equals 0, aka f of x is equal to 0. And similarly, as we already expect, if you get a factor such as x minus k, that means x equals k is a 0. So you've worked with these ideas a lot before, even if you haven't formalized them. So that allows us to figure out if something is a 0 really quickly, even if that something is not easily factorable. So for example, if this did have the factor x minus 2, that means x equals what would be my 0? We would expect x equals 2. So I'm expecting to see, does the point 2, 0 exist? That's really what the factor theorem and the remainder theorem are expecting us to find out. So let's try plugging in 2. I should get that when I plug in 2, the result is 0 if this is going to be an x-intercept. So I have 6 times 2 to the 4th minus 2 cubed minus 15 times 2 squared plus 2 times 2 minus 7. Now I do want to show you that there is actually a fairly fast way to check this in Desmos. Because if you were actually doing this on a homework, I would expect you to do this in the way that is going to cause you the least pain, essentially. So if I plug in f of x is equal to 6 x to the 4th minus x cubed minus 15x squared plus 2x minus 7, and if I literally check f of 2, it tells me that's 25. Or you could actually do out the multiplication kind of systematically yourself. So that's 6 times 2 to the 4th power minus 2 cubed Of course, I gotta give myself a little more room there. Minus 15 times 2 squared plus 2 times 2 minus 7. And that also gave us a result of 25. And really, this is very nice if you plug in a general f of x format and then on the next line you just actually check a 0. That will allow you on your homework to save yourself a lot of time and that you can just check multiple zeros at once, because let's say next I want to check 1, not a 0 if I want to check 0, not a 0 if I want to check 6, not a 0 if I want to check negative 2, not a 0, I want to check negative 1, not a 0. It just allows me to check a lot of zeros at once. And in particular, 2 doesn't work. And the way that you would say that is this result is 25. So that means I just figured out the point 2 comma 25 exists. An equivalent thing I just figured out that if I did this entire long division, then the remainder would be 25. So I don't actually have to do out the long division to know what that remainder is. That remainder is 25. And so it is not a factor. I know I have a remainder. I know I have a 0. X minus 2 is not a factor of this polynomial. Now I could check for a different polynomial, a different factor. So in particular, if x plus 2 is a factor, what 0 am I actually checking to see if it works? X equals negative 2. Go ahead and pause this video and see if you can check on your own. Is x equals negative 2 a factor of this polynomial? If so, why is that so? And if not, why not? So if you're going to check this, you want to use some sort of calculator, or I mean, you could just literally check it by hand, or go ahead and put that function into a calculator, and then you're checking the 0, negative 2 this time. And in that case, it worked. Indeed, when I plug in negative 2 to this function, the result is 0. Or if you don't believe the calculator, this is actually a small enough term that you can really check it on your own. So you're plugging in f of negative 2. So that's negative 2 cubed minus 6 times negative 2 squared minus negative 2 plus 30. Negative 2 cubed is negative 8. Negative 2 squared is positive 4. Times a negative 6 will give us negative 24. Minus a negative 2 becomes adding 2. Then we have plus a 30. Negative 8 minus 24 gets us negative 32. Negative 32 plus 2 gives us negative 30. Negative 30 plus 30 is indeed 0. We're okay. Now to figure out how it's going to factor from here, this is where I'm going to break out that polynomial long division that we just worked with. So we just figured out that yes, x plus 2 is a factor. How do we know that? Well, we know f of negative 2 is 0, which means that we will have a remainder of 0 when we actually do out this long division. And let's actually do the long division. So we got x plus 2 in here, x cubed minus 6x squared minus x plus 30. Now I want to do my long division algorithm. I'm going to ask myself, x times what will give me x cubed? So I can do that to the side. X cubed divided by x is x squared. Now I want to multiply x squared by x plus 2. X squared times x gets us x cubed. X squared times 2 gets us plus 2x squared. And then I want to subtract that entire result. So negative x cubed and a negative 2x squared. X cubed minus x cubed gets us 0 like I expect. Negative 6x squared minus 2x squared gets us negative 8x squared. And then you drop down the minus x and the plus 30. Now you repeat your algorithm. So you ask yourself, x goes into negative 8x squared how many times? Which is really asking you to do negative 8x squared divided by x. That gets you negative 8x. We're going to multiply negative 8x by x plus 2. Negative 8x times x gets us negative 8x squared. Negative 8x times 2 gets us minus 16x. And then we are subtracting the result. That was a minus 16x. I was about to write a plus. And when you subtract a negative, that becomes adding a positive. Subtract a negative, adding a positive. And since both x and 2 have the same sign, I should expect them to have the same sign whenever I'm subtracting over here. Negative ax squared plus 8x squared makes 0. Negative x minus plus 16x gets us positive 15x because we're doing a negative plus a 16. And then you drop down the 30. And then as a final result, you're going to ask yourself, x goes into 15x how many times? So 15x divided by x just leaves us with 15. You're multiplying 15 times x plus 2. 15 times x gets us 15x. 15 times 2 gets us plus 30. We subtract the 15x and subtract the 30. 15x minus 15x makes 0. 30 plus negative 30 also makes 0. So our result is x squared minus 8x plus 15. I'm going to continue this a little bit on the next page. So we just figured out that f of x equals x cubed minus 6x squared minus x plus 30 factors into x plus 2 times x squared minus 8x plus 15, because that was the result after our long division. Then I do want to ask myself, does x squared minus 8x plus 15 factor further? So I'm asking myself what's going to multiply to 15 and add to negative 8. That would be x minus 5 and x minus 3. And now I have completely factored this polynomial. So be careful that you don't just stop after the long division step if that result can factor further. Let's talk about complex zeros now. So for complex zeros, we first want to remind ourselves what is a complex number. So before, when we ran into the situation of something like the square root of negative 4, we said, hold up, we don't know how to do that because we have a negative under a root. So it's not a real number. However, we can write an imaginary number in its place where we start talking about I. So in particular, I by definition is the square root of negative 1. So if I have something like the square root of negative 4, I can state that's the same thing as the square root of negative 1 times the square root of 4. The square root of negative 1 by definition is I, and the square root of 4 would be 2. And then typically we would write that the other way around. Instead of saying I times 2, we tend to just say 2 times I by convention. And that's how we would express the square root of negative 4, because a negative 1 underneath the square root, we just call an I an imaginary number. And that is how I rewrite some sort of complex number as an imaginary number in general. I'm going to break up the square root of a negative. Instead of just saying he's not real, I'm specifically going to say which not real number is he. The square root of the positive version of the number times the square root of negative 1. I'm going to rewrite the square root of negative 1 as I. So if I have the square root of negative 9, I will rewrite that as the square root of 9 times the square root of negative 1. That's okay by the rules of how square roots work. I am allowed to break up any multiplication underneath the square root into 2 separate square roots. Then I can state the square root of 9 is 3, and the square root of negative 1 by definition is I. And that would be my final answer. Go ahead and try to rewrite the next one yourself, and go ahead and try to challenge yourself to simplify that square root as well. So the square root of negative 24 I will rewrite as the square root of 24 times the square root of negative 1. The square root of negative 1 I know is I, and then I want to figure out how does the square root of 24 simplify. So a tool I often use is by factoring this guy out. So I ask myself, what multiplies into 24? Maybe I come up with 12 and 2. Then I ask myself, do either of these break down further? 2 is prime, so I can't break him down. But 12 further breaks down into 6 and 2. And then 6 further breaks down into 3 and 2. So I've completely prime factorized him. Then I note who comes in a pair, which is the 2's. And then who's going to stay by himself on the end of this? and that is the 3 and the 2. Anything that was sort of a middle step that I broke down further, I'm going to ignore those numbers. So I can rewrite the square root of 24 as the square root of 2 times 2 times the square root of 3 times 2, and then I still have my I from that square root of -1. The square root of 2 times 2 is the square root of 4, which is just 2, so some people sort of skip that step and they go ahead and just write whatever has a pair out front of the square root. And then 3 times 2 gets us 6. The square root of 6 does not break down further. And then we have an I. I sort of note that the I is not underneath the square root really explicitly, because you do want to make sure that it is known that that is not underneath the square root. And sorry that my computer just spazzed out there for a second. But that is the final answer for what that looks like there. There we go. So completely break it down using a factor tree, simplify your square root. Anything that is a negative underneath the square root means that you have to pull out an I to indicate that is a negative underneath that square root there. Let's see what happens when we multiply complex numbers. And in particular, this first set has a special relationship of being a conjugate, while the second set does not. So I want us to notice what's sort of different whenever I FOIL out each of these sets. So let's do the first one first. So I just want to multiply it out like normal. So I do 3 times 3 gets us 9. 3 times -2i gets us -6i. Positive 2i times 3 gets us positive 6i. And positive 2i times -2i gets us -4i squared. Now let's start to simplify this a little bit further. What are some like terms I can combine? Well, -6i plus 6i makes 0, so I'm really just left with 9 minus 4i squared. And now it's going to be helpful to remember what I is by definition. What is the definition of I? Well, I is the square root of -1, so I'm going to rewrite that explicitly. Now when I square a square root, that undoes one another. So I'm just left with 9 minus 4 times the square times -1, because I just undid the square and the square root. -4 times -1 gets us positive 4, and my result is just 13. There's actually no i's left. Let's see if a similar thing happens with the other one. So if I do 5 times 5, that gets us 25. 5 times -2i gets us -10i. 3i times 5 gets us +15i. And 3i times -2i gets us -6i squared. Go ahead and pause this video and try to simplify this as much as possible. So when you were simplifying, hopefully you noticed that -10i and 15i are like terms, although this time they don't just cancel out. I'm just going to be left with +5i. And then hopefully you rewrote I squared as the square root of -1 squared. Then you notice that squaring a square root undoes each other. And I'm left with -6 times -1. -6 times -1 leaves us with +6. And now 6 and 25 are like terms, so I have 31 plus 5i as my final answer. And that gets into what situations you would end up with both a real and imaginary part back in the definition of a complex number. So this is entirely considered one number, where the 31 is the real component and the 5i is the complex component, or the imaginary component, I should say, to make one complex number. So let's use this knowledge in order to find complex zeros of quadratics, which before we would just stop and say they're not real. Now we're going to be able to talk about which not real numbers they are. So for the first problem, you might first ask yourself if this is factorable. So if anything multiplies to 10 but adds to 6, unfortunately not, so we have to break out the quadratic formula. You might want to know what a, b, and c are in the quadratic formula. So a is 1 because there's secretly a 1 in front of that x squared. B is 6 and c is 10. The quadratic formula is x is the opposite of b, plus or minus the square root b squared minus 4ac all over 2a. and then we just want to start plugging it in. So x is the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. And now we just start simplifying each and every part of this. So we have x equals, we're not touching that -6 yet. 6 squared gets us 36. 4 times 1 times 10 gets us -40. All over 2 times 1 is 2. 36 minus 40 gets us -4. Now we want to simplify the square root of -4, so that becomes -6 plus or minus the square root of 4 times the square root of -1. The square root of 4 gets us 2. And the square root of -1 by definition is I. Now at this step, we're able to say that there's a number that goes into -6, 2, and 2. We can divide all three terms by 2. And when you do that, you're not touching the I, you're kind of treating it like a 2x divided by 2 is just x. So -6 divided by 2 is -3. Positive 2i divided by 2 is just going to give us I. And 2 divided by 2 is 1. So we really won't write the divided by 1 part anymore. So just our final answer is -3 plus or minus I. So we have two answers, -3 plus I, -3 minus I. For this next problem, since we have no b term, I would say the easiest way to find these zeros, and really we were saying the other one equal to 0 as well. So the easiest way to find these zeros is just to undo the square with the square root. So in order to get x squared by itself, we would first add 20 to both sides. We're left with -2x squared is equal to +20. Then we would still want to get x squared by itself, so we would be dividing by -2. X squared is equal to -10. Then we undo with a square root and use plus or minus. So x is equal to plus or minus the negative square root of 10. We can rewrite the negative square root of 10 as the square root of 10 times the square root of -1. We might ask ourselves if the square root of 10 breaks down further, but 10 just breaks down into 5 and 2. There are no repeated numbers. There are no perfect squares that go into 10. So that's just plus or minus the square root of 10, and the square root of -1 becomes I. So plus or minus the square root of 10i. So we literally have the square root of 10 positive I and negative square root of 10i as our two answers, which most likely you would just see written as the plus minus, but keep in mind that means two different answers. So the big thing that we're able to do now that we weren't able to do before is now we can actually talk about specifically which not real numbers, which complex numbers are solutions. And we can continue to find them in other situations by factoring as well. So this first one seems like a great example of where we could use U-substitution in order to factor this, because in particular, if I make U equal to half of x to the fourth, x squared, that would make U squared x to the fourth. So I can rewrite this as U squared minus 9. And then from here you could either factor it or you could undo the square with a square root. Either way would be fine. I will actually just show you both ways, so because both ways are totally valid and might be more useful in certain situations. So if we're going to undo with the square root property, our goal is to get U by itself, so we will add 9 to both sides. -9 plus 9 makes 0. I'm left with 9 is equal to U squared. Then we want to undo that square with a square root. And then we get plus or minus the square root of 3 is equal to U. And then we have to remember what U actually is. So U is actually equal to, oh, sorry. Let's back that up. I just made a grave mistake. What mistake did I just make? Pause your video and figure out my mistake. The square root of 9 is 3. I don't know why I just rewrote the square root already. So we already noted that the square root of 9 is 3. So the result is plus or minus 3. Because I'm doing that plus or minus square root of 9. So the result is positive or negative 3. So either u is equal to 3 or u is equal to negative 3 if we're going to really break it down as the two solutions if u squared is equal to 9. Now I want to note what u is. U is equal to x squared. So either x squared is equal to 3 or x squared is equal to negative 3. So now we'll go one step further, undoing the square with the square root again. And whenever we undo with the square root, we have to plus or minus. So x could be the positive square root of 3, could be the negative square root of 3. Or when we're dealing with the negative square root of negative 3, that would be the square root of 3i, or the negative square root of 3i. So there are 4 solutions for this x to the 4th problem. The second way to do this would be to factor him. So I could say that u squared, so way number 2, if I have 0 is equal to u squared minus 9. I know that this factors into u minus 3, u plus 3, because I'm asking myself what multiplies to negative 9 and adds to 0. So if I now set up my two mini equations, I either have u minus 3 is equal to 0 or u plus 3 is equal to 0. For the first mini equation, I want to add 3 to both sides to undo subtracting 3, so u could be 3, or minus 3 to both sides for the other one, so u could be negative 3. Then I want to replace u with what he actually is, which is x squared could be 3, or x squared could be negative 3, and now I'm back to the exact same thing that I had before, where I'm going to now undo that square with the square root. When I undo a square with a square root, I want to do plus or minus, so x is positive square root of 3, negative square root of 3, positive square root of negative 3, negative square root of negative 3, and we want to rewrite the square root of negative as the positive and the I. Negative, so square root of negative 3 gets rewritten as square root of 3i, and then those regular solutions just drop down. So those are our 4 solutions. Either way, whichever way you like better in order to solve it is fine. If you're able to sort of conceptualize factoring with writing x squared directly in terms of instead of u, you could do that as well. Just make sure that you're still consistently getting the correct answer. So let's do the same thing with this next one. So for this next one, we want to pick our same u and u squared. Our u would still be x squared, which would make u squared x squared squared, which is x to the 4th. So I want to rewrite this in terms of u, so that becomes u squared plus 2u minus 3. Go ahead and pause your video and see if you can take it away from here to find all of your zeros. Hopefully from here you asked yourself what multiplies to negative 3 but adds to positive 2, and that would be positive 3 and negative 1. Then you set up your two mini equations, so either u plus 3 is equal to 0 or u minus 1 is equal to 0. Then you subtracted 3 from both sides for the first mini equation for u is equal to 3, then equal to negative 3. In other words, you added 1 to both sides to get u is equal to positive 1. Then you replaced u with what it actually was, which is x squared being negative 3 or x squared being positive 1. Then you undo a square with a square root, plus or minus when you undo a square with a square root. So x could be the positive square root of negative 3 or the negative square root of negative 3. Or x from the other one could be the square root of 1 is just 1, so positive 1 or negative 1. And when we're taking the square root of a negative 3, we want to rewrite that in terms of I. So that's square root of 3i, negative square root of 3i, 1 or negative 1 is all of our solutions. So the linear factorization theorem is really a continuation of the factor theorem we were already thinking about before, which is to say that if a polynomial function will have the same number of factors as the degree. So this is to say if I were to completely expand out, so like if it factored into x minus 2 all squared, being x minus 2 times x minus 2, that would correspond to a quadratic, for example. Quadratic. So by this, they don't mean that all of those have to be unique factors, but I can eventually break it up into as many parentheses as there are degrees in the polynomial. So for example, in x to the 7th as the highest term, I would expect to have 7 sets of parentheses. And each factor will be in the form of x minus c, where c is a complex or real number. So what's really taken one step further here is that I'm kind of conceptualizing I could have like an x minus 2i, for example. While before I would just run out of real solutions, now I can talk about what type of non-real solutions we have. If a polynomial function has real coefficients and a complex zero of the form a plus bi, then it also has the complex conjugate a minus bi. So let's actually pause there because it's sort of a hidden, really powerful idea. And let's actually look at some of our previous examples here. So for example, when the square root of 3i was a 0, the negative square root of 3i was also a 0. And if we look at up here, when I had negative 3 plus I was a 0, the negative 3 minus I was a 0. And that really comes from this plus or minus square root part of the quadratic formula. Because the only way that a complex number even appears in a solution is if I have plus or minus a negative underneath a square root at some point. And that happens regardless if I use quadratic formula or if I'm using the square root property and undoing a square with a square root. At some point, if I have the positive version of that complex number, I'm also going to have the negative version of that complex number. Even if that real part, in fact, that real part will always stay the same. So that plus minus part in the quadratic formula is not attached to the real component. That real component keeps his sign. He keeps the exact identical thing. So if, for example, 4 plus 2i is a 0, what else has to be a 0? 4 minus 2i. If, for example, just to really hone in the point, negative 5 plus I is a 0, what else is a 0? Negative 5 minus I, so that negative 5 part stays the same. Or if I gave it to you kind of the other way around, if I had negative 3 minus 4i is a 0, what else is a 0? Negative 3 plus 4i. And those are those complex conjugates. And that's really tells you a lot about the polynomial. And we can combine all of this knowledge in order to find what the polynomial function actually is. So let's look at this kind of in an example, and I'm going to backtrack and kind of explain these steps. So let's say this was an example problem, and this is a really accurate idea of like what an example problem might look like on a test. So we have a degree 4 polynomial with the zeros negative 3, 2, and I. And then they also give us another point, f of negative 2 is 100. So they really gave us the point negative 2, 100 as an additional point. Well, first of all, it's a degree 4 polynomial and we're missing a 0. What else has to be a 0? Negative I also has to be a 0 because positive I is a 0. So we know this because if I is a 0, its conjugate negative I is also a 0. Remember, zeros are just different names for x-intercepts. And now let's think about what this function would look like. So I have the f of x is equal to some unknown multiplication factor that wouldn't impact its zeros, some number chilling out front. If negative 3 ends up being a 0, what would be my parenthesis? X plus 3. If positive 2 is a 0, what would be in parentheses? X minus 2, both of those are factors. And then we can kind of similarly talk about the i's. So we have an x minus I, and then for the last one, an x plus I. And since we want real coefficients, it's okay if we don't touch these two parentheses. Those are already entirely real. But what we don't want is a bunch of i's showing up. So we need to expand out just this part that has i's in it. So for now, I'm just going to rewrite the other parts. And now let's expand out the part that has i's in it. So when we do x times x, that'll get us x squared. X times I gets us plus ix. Negative I times x gets us minus ix. and negative I times I gets us minus I squared. And now we want to simplify these complex numbers. Ix minus Ix makes 0, thankfully. And I, by definition, is the square root of negative 1. And once I square the square root of negative 1, that will undo each other. I'm left with x squared minus a negative 1. And that becomes x squared plus 1. And then you could really confirm backwards to make sure that you get the 0 you're expecting. Because if I have x squared plus 1 is equal to 0, if I were solving backwards, I would subtract 1 from both sides. X squared is equal to negative 1. Then I would undo a square with a square root and plus or minus. So x equals plus or minus the square root of negative 1, which means plus or minus I by definition. That's what I was expecting to happen. So I know I'm good. And then I'm just going to drop down the other part. So I've now written most of my polynomial, and this is actually why I gave you more room. So because if I did not give you, this was a specific point, and I just said write a polynomial such that this is true, you would have all these parentheses, make a1, and call it a day. But we have more information, because we also know that since f of negative 2 is equal to 100, I can actually plug in the f of negative 2 should be plugging in negative 2 for all these x's. So we have negative 2 plus 3, negative 2 minus 2, negative 2 all squared, plus 1. And that was, again, because we had narrowed down that our function must look like some unknown multiplication factor, x plus 3, x minus 2, x squared plus 1 is my 3 factors. They told us here that specifically f of negative 2 is equal to 100. So I know 100 is equal to my unknown multiplication factor times negative 2 plus 3 is 1. Negative 2 minus 2 is negative 4. Negative 2 all squared is 4, and then there's still a plus 1 in that parentheses. So I have 100 is equal to that multiplication factor. 1 times negative 4 is negative 4. 4 plus 1 is 5. Negative 4 times positive 5 is negative 20, and we're multiplying that by a. I just flipped around the order since we're used to seeing the a behind. And then we undo multiplying by negative 20 by dividing by negative 20. So my unknown multiplication factor is negative 5. So we can finally write out that this polynomial would be f of x is equal to negative 5 times x plus 3 times x minus 2 times x squared plus 1. And on an exam, you would definitely be expected to just keep it in that form, but you do have to multiply out the x plus I, x minus I because of this real coefficients part. So you're not allowed to keep that as is. But things like x plus 3 and x minus 2 you should definitely keep as is. And just like before when we were dealing with real zeros, once you have your parentheses made with all real coefficients, that's where you stick the unknown multiplication factor a out front and solve for him. So let's backtrack to those written steps to sort of see how those worked. So the first things we did was construct our linear factors. So that was that x plus or minus some sort of number. And then whenever we had imaginary ones, we wanted to multiply that out. And that would also still apply even if there was a more complex imaginary number going on. And when you have a more complex imaginary number going on, you're going to want to definitely keep track of those parentheses really, really carefully. You want to leave some sort of stretch factor out front. We usually call it a, that you are going to solve for. Substitute in your point to solve for a. Then write your polynomial. If it says to expand it out, you can expand it out. That's just usually beyond the scope of what you're required to do on test. So I want you to pause your video and try this next one out for yourself. So here we want to note what all of our zeros are. So they gave us that 5 and 2i was 0. So what else has to be a 0? We also know that negative 2i has to be a 0. So if we're setting up our parentheses, we have f of x is equal to an unknown multiplication factor, x minus 5, x minus 2i, x plus 2i. Now we want to make sure that for those complex parentheses that we multiply that out. So we have x times x gets us x squared, x times 2i gets us plus 2ix, negative 2i times x gets us negative 2ix, negative 2i times 2i gets us minus 4i squared. 2ix minus 2ix thankfully gets us 0, and I squared, we recall, is the square root of negative 1, all being squared. The square root of negative 1 squared undoes each other to get us negative 4 times negative 1. Negative 4 times negative 1 gets us positive 4. Now we might want to kind of confirm off to the side that that gets us the complex zeros we're expecting. So for x squared minus 4, we subtract 4 from both sides. That gets us x squared is negative 4. Then we undo a square with a square root, plus or minus. So x is equal to plus or minus the square root of negative 4. So that is plus or minus the square root of 4 times I because of that negative. And the square root of 4 is indeed 2. So we do get plus or minus 2i. We are a-okay. And then we can just drop down the rest of it. Now we want to plug in the specific point we were given. In this case, it was f of 1 is equal to 10. If they didn't give us a specific point, just make a 0 and keep it generic. But here they gave us that was 10 specifically, and there is enough room to write on 2 pages, so that's what we're going to do. So we're going to plug in that now we know that we're going to plug in, let's just even be more explicit, we're going to plug in f of 1. And our goal is to solve for a, so we're replacing x with 1. They gave us the f of 1 is 10. 1 minus 5 gets us negative 4. 1 squared is 1. 1 plus 4 gets us 5, of course. Negative 4 times 5 gets us negative 20. Then we divide both sides by negative 20 to undo multiplying by a by negative 20. 10 divided by negative 20 is a fraction that simplifies because both of the top and the bottom are able to be divided by 10. 10 divided by 10 gets us 1. Negative 20 divided by 10 gets us 2. So a is equal to negative 1/2. Then we remember to plug it all back in, so we have f of x is equal to negative 1/2 x minus 5 times x squared plus 4. And that would be our fully factored final answer for our polynomial. Oftentimes you're not necessarily given the zeros though. You might have to do a little bit of work to find them. And there's a very nice rational zeros theorem that allows us to narrow down our potential zeros of any sort of polynomial. This is a small proof about why it works, but the short of it is that you do plus or minus all the factors of the constant divided by all the factors of the leading coefficient. For reasons that are in math history that I should probably know what they are, but I don't. For whatever reason. The factors of the constant are labeled as p. The factors of the leading coefficient are labeled as q. I don't find p over q to be super meaningful. I tend to think of it as factors of the constant over factors of the leading coefficient. Or if you want something a little bit shorter to remember, it'll be last over leading. Is really what you need to remember is how it works out to be. So all the factors of the last term over all the factors of the leading term. If in doubt and you can't remember which way around it works, pick a nice quadratic that it has to work for. Let's say like x squared minus 9. Hopefully you've worked with something like this enough to know, okay, this factors into x minus 3, x plus 3, so my two zeros are 3 and negative 3. Which would be factors of your last term, 9. So that'd be last over leading. So those could be kind of rewritten as 3 and negative 3 over 1. So that's a way to remember it's the last one, is like fall back on some sort of example where you know how it's supposed to work, and that'll help you keep it straight. So let's just practice listing all these. So our p, which is our last term slash constant, factors. Let's list all those out. So in this case, what is considered our constant? That would be -4. And where are all the factors of -4? Well, we have 1, we have 2, and we have 4. Great, now let's do the leading term. So Q, that's our leading term. In this case 2, and what are all the factors of 2? 1 and 2 are it. Now we put it all together for this P over Q, last over leading, and then you just need some sort of system to systematically divide them. So we do 1 divided by 1, then 1 divided by 2. Then you move on to the next term. 2 divided by 1, 2 divided by 2. And even though you'll notice that we're starting to repeat stuff, I don't simplify just yet. I simplify at the end. And then you do the last term, 4 divided by 1, 4 divided by 2. Now you start to simplify these guys. So 1 divided by 1 is 1, 1 divided by 2 is a half, 2 divided by 1 is 2, 2 divided by 2 is also 1, and we already wrote that down. 4 divided by 1 is 4, 4 divided by 2 is also 2, and we already wrote that down. Which, if plus or minus is not a notation that you want to use, that means we found out the only rational zeros, which are basically saying the only zeros that can be written as nice, clean fractions. So we're not talking about i's, we're not talking about the square root of 2 or something like that that doesn't simplify. Nice, clean fractions are 1, -1, a half, -1/2, 2, -2, 4, and -4, which does seem like a long list, but if you recall that Rational Zeroes Theorem, this is Rational Zeroes, sorry, the remainder theorem, you know if you plug any of these guys in that you should get 0 if they're going to be a factor. So if you're just told to cold factor this and you're like, oh my gosh, that seems impossible, I don't even know where to start. Where you want to start is by putting the polynomial into some sort of calculator, and then you just want to start your educated guessing and checking with this limited list that you just made. So you would plug in f of 1, for example. That would get you -6, not a factor. Then you try -1. That's 4, not a factor. Then you try a half. -4.25, not a factor. Then you try -1/2. -3, not a factor. Then you try 2. -8, not a factor. Then you try -2. 72, not a factor. Then you try 4. 204, not a factor. Then you try -4. 844, not a factor. And I think I forgot -1/2. Yep. So none of those were nice rational factors. And actually, if you click on this polynomial, he doesn't have any nice rational factors. So none of those actually were factors in this case, because the only factors of this polynomial are funky numbers that cannot be written as nice clean fractions. But if there were anything that could be written as nice clean fractions, it would be restricted to that list. Go ahead and list all the possible rational zeros for this next one, and then compare with what we get. So here, for that last term, that's just 1. And what are the only factors of 1? Plus or minus 1. For the leading term, in this case, that is 2 again. So what are his factors? That would be plus or minus 1 or 2. So if we're listing all of the potential ones, well, that would be plus or minus 1 divided by 1, plus or minus 1 divided by 2, and that's it. It's just last over leading. So your only potential factors are plus or minus 1 divided by 1 is 1. A half is already simplified, so literally 1, -1, a half, or -1/2. So if any of these were going to be factors, if there were any rational factors of this polynomial, things that are not funky square roots, things that are not complex numbers, it would have to be one of these guys. And we could check on some sort of graphing calculator by putting in the function. You want to also define that the function, we're going to call it f of x or f of something, and then you would check this nice limited list. So for example, +1 now does work. It evaluated to 0. I could also click on the graph and confirm that. Also -1 does not work. A half does not work. Negative a half does not work. But so I just narrowed down. There's only one nice rational factor. That's just one. The other ones, the other zeros are funky. They're not going to be written as nice clean fractions. One is the only zero that is a nice clean fraction. And that does help you factor these completely, because now that you know x equals 1 as a factor, then you could go ahead and divide this guy by x minus 1 in order to figure out what those other factors are. And that's exactly what this is getting at. So why is this useful? It gives you a way to educatedly guess and check for some initial zeros, for any zeros that can be written as nice clean fractions, not as funky square roots that can't be simplified further, not as complex numbers, but nice clean fractions or whole numbers, rational numbers. That's where the name comes from. Rationals are just things that can be written as fractions. So you use that to find all the possible rational zeros. Then you educatedly guess and check by plugging those in. You want to use the fact that you have a graphing calculator to your advantage, plug it into f of x or something, and then plug it into the next line. And then once you find something, like for example for this first one, since we know that 1 is a factor, we could divide this guy by x minus 1 in order to figure out how this guy completely factors. So let's look at this as an example. And then this is a good example where I could do the process I just did. But this guy might just be factorable. And you don't want to forget that, even though we have these other techniques. Is this guy factorable? Well, let's check out. So this has 4 terms. We want to check if he factors by grouping. For the first group, what's his greatest common factor? 3x squared. If I do 3x cubed divided by 3x squared, that will leave me with just x. 3x cubed divided by 3x squared. 3 divided by 3 is 1. X cubed divided by x squared is x. Similarly, if I do 9x squared divided by 3x squared, 9 divided by 3 is 3. X squared divided by x squared is 1. So that just leaves me with 3. X and 3, what's their greatest common factor? That's just 1. And now I can make one parenthesis of what's the same, x plus 3, and one parenthesis of what's different, 3x squared plus 1. And if my goal is to find all the zeros, then I want to set this guy equal to 0. One mini equation is just x plus 3 is 0. The other mini equation is 3x squared plus 1 is 0. For x plus 3 is 0, I want to subtract 3 from both sides, so x is negative 3. For 3x squared plus 1 is 0, I want to subtract 1 from both sides to undo adding 1. 3x squared is equal to negative 1. Then I divide by 3 to undo multiplying by 3. X squared is equal to negative 1/3. How do I undo a square? I square root and plus or minus, so x is equal to plus or minus the square root of negative 1/3. I want to rewrite that in terms of I, so it's plus or minus the square root of 1/3 I. So our total zeros are negative 3, the positive square root of 1/3 I, and the negative square root of 1/3 I. We don't go into rationalizing in this class, so I am completely okay with you just leaving that as is. For this next one, he's unfortunately not going to be factorable. You might be really tempted to say he is, but you have to notice that this first term is a third and not a square. So you can't just do the AC method in this case. So for here, this is where it's going to be helpful to educatedly guess and check by making our list of potential rational zeros. So I want to look at P, which is our last term's factors. In this case, our last term is negative 1, so his only factors are plus or minus 1. Q for the leading term, which in this case is 4, so plus or minus all the factors of 4, which would be 1, 2, and 4. And now I want to combine that to make my actual list of potential factors, so 1 divided by 1, 1 divided by 2, and 1 divided by 4. And those are pretty much simplified, except for 1 divided by 1 simplifies to 1. And now I have a list of 6 terms to educatedly guess and check if they're going to be zeros. So that's when I want to break out my graphing calculator, but now it's 4x cubed minus 3x minus 1. These are also small enough numbers that you could just like try it for yourself. And lo and behold, I already happen to have f of 1 is in there, and 1 is indeed a factor because it equals 0. If I plugged in -1, not a 0 because that equals -2. But positive 1, x equals 1, is a 0. So since f of 1 is 0, x equals 1 is a 0. We know the point 1, 0 exists. So what does that mean that we know is a factor in terms of our parentheses? Well, we must have a factor of x minus 1 to get that result, because if you're kind of thinking backwards, that would result in the mini equation of x minus 1 is 0, so x equals 1. So since I know x minus 1 is a factor, I can divide this guy by x minus 1. And this is a case where I like to put in a placeholder value of 0x squared to make sure I don't just get my placeholders mixed up, since there is nothing written in between the x cubed and the x. Now I do polynomial long division like I've been doing. So I ask myself, and this does have 2 pages, cool. So I ask myself, x goes into 4x cubed how many times? So this is asking me to do 4x cubed divided by x. That gives us 4x squared. And then I want to multiply 4x squared by x minus 1. 4x squared times x gets us 4x cubed. 4x squared times -1 gets us minus 4x squared. And then I'm subtracting that result. So I'm doing minus 4x cubed plus 4x squared. And if the signs are mismatched on what I'm dividing by, they should be mismatched on what I subtract down here. So 4x cubed minus 4x cubed gets us 0 like we expected. Drop down the 4x squared. Drop down the minus 3x. Drop down the minus 1, since 0x squared plus 4x squared just results in 4x squared. Now I repeat. So I want to know x times what will give me 4x squared. So I do 4x squared divided by x. 4x squared divided by x gets us 4x, so I'm adding 4x. Then I do 4x times x minus 1. 4x times x gets us 4x squared. 4x times -1 gets us minus 4x. Then I subtract that entire result. So that's minus 4x squared. Minus a negative becomes adding a positive. So minus 4x squared plus 4x. 4x squared minus 4x squared makes 0. Negative 3x plus 4x makes x. Drop down the -1. Then hopefully in this case you should kind of already know something nice is happening, but I could formally ask myself, x goes into x how many times? X divided by x is 1. Multiplying something by 1, 1 times x is just x, 1 times -1 is just 1. And then when I subtract that entire result, that becomes minus x plus 1. And both of those do indeed make 0 just like I want. So what I just figured out is that it's the first step that this factors into x minus 1 times 4x squared plus 4x plus 1, because that was the result of that division. I'm not done yet though, be careful, because now I want to ask myself if this next part further factors. So this would be the AC method. So that'd be 4 times 1, which is 4, but add to b, which is 4. So what's going to multiply to 4 and add to 4? That would just be 2 and 2. And since there is a leading coefficient out front, I can't just jump straight to my parentheses. So I'm going to have to break up that middle term into 2x and 2x. Drop down the other terms, 4x squared and the 1. Now I'm going to start factoring that part by grouping. The greatest common factor of 4x squared and 2x is 2x. 4x squared divided by 2x is 2x. 2x divided by 2x is 1. The greatest common factor of 2x and 1 is 1. Dividing both of those by 1 leaves you with itself. One parenthesis of what's the same is 2x plus 1. And in this case, the other also happens to be the same, 2x plus 1. And then I want to drop down the rest of it. And since I'm finding zeros, I want to set f of x equal to 0. And now I can solve. So for the first parenthesis, I'm just going to reconfirm what I already found out by the remainder theorem, that x minus 1 is 0. Means x equals 1 is one of my zeros. The next two are actually repeats of each other, so this kind of has a multiplicity of 2. Or not kind of, it does have a multiplicity of 2. Subtract 1 from both sides, so 2x is equal to negative 1. Divide by 2, x is equal to negative 1/2. So my total list of zeros are 1 and negative 1/2. 1 has a multiplicity of 1. Negative 1/2 has a multiplicity of 2. The fundamental theorem of algebra is, of course, extremely fundamental to the study of algebra. So let's go over what that says. So for the fundamental theorem of algebra, if we have a polynomial, it says of degree greater than 0, so we're talking about something that's not just a straight across line like y equals 4, so a polynomial that at least has an x in it, then the polynomial has at least one complex zero. And keep in mind when they say complex zeros, that real numbers are special complex numbers. So all real numbers are complex, but not all complex numbers are real. So all Lindenwood students are college students, but not all college students are Lindenwood students. Complex numbers are the bigger umbrella. We can use this theorem to argue that if the polynomial has a degree where there's at least one x, then if we have a 0, then we can break it into a whole bunch of parentheses times some sort of multiplication factor out front, and that could be a 1. So essentially break it up in the same way that we've been breaking up all of our polynomials, where we have a big old set of parentheses. If we don't consider things with multiplicities to be if we do consider things with multiplicities greater than 1 to be kind of their own separate parentheses, write them separately. So like for this 4x to the cubed one, I could have also just written that as x minus 1 times 2x squared. 2x plus 1 all squared. But if I break it up completely, I've got 3 sets of parentheses for a degree 3 polynomial. When I had a different example earlier, we had a degree 3 polynomial where I could have also written that as x plus 3 times x minus the square root of 1/3 I, x plus the square root of 1/3 I. That would be the really like extra way of writing it with non-real coefficients, but that would be again a degree 3 polynomial with 3 parentheses. So the degree will match however many parentheses you have, maybe with a number out front. That's again something we've kind of seen but not named. So we have that many roots, so whatever the degree is equal to the number of roots if we also include multiplicities. So you've already seen this. If I have an x squared, I should have at most 2 roots slash zeros slash x-intercepts. So roots, zeros, x-intercepts, they're all words for the same thing, tomato, tomato. If it's x squared, I'm going to have 2 of them. If x to the 10th is my leading term, how many of them am I going to have? 10. Some of them might be complex, some of them might repeat, therefore have a multiplicity bigger than 1, but you're going to have 10 of them. That's all this is saying. So let's take a step back and look at like an example of a problem that would require you to apply the fundamental theorem of algebra. So let's say my Chihuahua Eldon has gotten into math a lot lately. He says it's possible for a degree 4 polynomial to have the zeros 3, 4, -5, and 5i. Is he correct? So pause your video and think about, is he correct or not? He is not correct. Why is he not correct? Well, if 5i is a 0, then -5i is also a 0. Now we have 5 zeros, but a degree 4 polynomial can only have how many zeros? 4. And not only can it have that many zeros, it will have that many zeros. Has 4 zeros. Maybe not unique, but it has 4 zeros at some point. 4 parentheses I would break it down into. So this is false for exactly that reason. So a lot of times with this fundamental theorem of algebra, it's an idea you've seen before. the degree of the polynomial should equal how many zeros I have, saying that multiplicity means they're different zeros because I could break it up into separate parentheses. And complex zeros come in pairs. That's the other big idea. If you understand those two ideas, degree 4 polynomial should have 4 zeros, degree 10 polynomial should have 10 zeros. If 5i is a 0, negative 5i is a 0. If 2 minus i is a 0, 2 plus i is a 0, you're good. That's what the mathy complex theorems of this section say, are those ideas that you've still seen even if you haven't named them. What are some other kind of example problems that you could have to do with this? So let's just kind of wrap this together. So find a polynomial of degree 4 with real coefficients and the following zeros, 2 and I. What else would have to be a 0? Well, you know negative I is also a 0. So we know we can break this into x minus 2, x plus I, and x minus I. It just says a polynomial, so in this case we're sort of in the habit previously of sticking an a out front, solving for him. Since it just says a polynomial, make a equal to 1. Why not? Make your life easier. If I just kind of paused here and expand, and actually let's say I just paused here, what would be my issues? I would have several issues. First of all, I need real coefficients. So I'm going to have to simplify this. What's my other issue? Right now I've written a degree 3 polynomial actually. So I need to somehow make this into a degree 4. And the best way I could think to do that is, well, technically it doesn't say that you can't just make up a different unique 0, so you could do that. Or I would just stick a multiplicity of 2 on that x minus 2. Call it a day. So 2 appears twice. Great. Bounces off the graph at that point. It just touches the graph at that point, however you want to phrase conceptualizing. That would look like over here at 2, they would just touch like that. And now let's just expand this out. So let's keep going. So for the first part of it, I would just leave the x minus 2 all squared exactly as is. And then I would expand out this in order to figure out what those real coefficients are going to be. So you do x times x is x squared, x times I is minus ix, I times x is plus ix, I times negative I is minus I squared. Again, keep the first part the same. Negative ix plus ix makes 0. I, by definition, is the square root of negative 1. If I take the square root of negative 1 all squared, that undoes each other. I'm left with x squared minus negative 1, which is x squared plus 1. And then the other terms I'm just dropping down. And then I might want to confirm to the side, hey, does x squared plus 1 gives the zeros we're expecting, so you undo adding 1s by subtracting 1 on both sides. X squared equals negative 1. Then you undo a square with a square root, plus or minus, so x is plus or minus the square root of negative 1, and the square root of negative 1 by definition is I. We're good. So we just came up with a degree 4 polynomial with the zeros of positive 2, I, and by extension of I being a 0, negative I. And you're good. This is an example of kind of tying this all together that might appear on your homework. So we have some degree 11 polynomial with coefficients that are real numbers, and we have these zeros. What else do I know has to be a 0? There's kind of two possible answers you just could say here. From this first part, you also know negative 2 plus 4i is a 0. And from this next part, you also know negative 5i has to be a 0. So either of those would be equally correct answers because you know those 4 zeros occur. Then it says, what is the maximum number of real zeros this could have? So I think it's good to sort of conceptualize what's going on here. If it's degree 11, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros spots. We've already taken up some of those with we have negative 2 minus 4i and negative 2 plus 4i. We have 9 left. Then we also have 5i and negative 5i. Now we have 9 minus 2 is 7. So we've got 7 left. So we've still got 1, 2, 3, 4, 5, 6, 7 mystery spots. So I could have at most 7 remaining real zeros on this polynomial. If I said there were 7 potential remaining non-real zeros on this polynomial, what's the problem with that statement? Pause your video and think about what would be the problem. Well, the problem would be, let's just make up some potential non-real zeros. So let's say we had 1 minus I as a non-real zero. What else would be? 1 plus I. Let's say I had negative 2i. What else would be a zero? 2i. Let's say I had 4 plus 6i. That would also have 4 minus 6i. And oh my gosh, I only have one more spot left. So if I said something like I would also need negative I, and oh my gosh, now I am down to a degree 12 polynomial, so that doesn't work anymore. So really, the most I can have is exactly what I just wrote out there, 6. I could have at most 6 non-real zeros. Now I'm going to do an example of what would be sort of the trickiest type of problem that you could be given. Because some of the arithmetic in between can be a little bit tricky, so you just have to be really careful about how you keep track of things. So let's see an example of that. So let's say I knew that negative 3 plus 2i is a 0. Well, what else do I know has to be a 0? That means that if negative 3 plus 2i is a 0, negative 3 minus 2i also has to be a 0. So let's expand out what we just figured out were some factors of this. So I know I have x minus negative 3 plus 2i and x minus negative 3 minus 2i would have to be those. You might be thinking to yourself, well, before, if you did a plus and minus situation, it will eventually sort of boil down to that. But keep in mind the theorem still says we have x minus c as our linear factor. So if negative 2, for example, is a 0, I broke that into x minus a negative 2 at some point that I just automatically was able to jump to being x plus 2. These are unique enough that I don't know how to just jump to exactly what's going to be inside my head without first actually doing the expansion myself. So let's just first expand these negatives. So a negative 1 times negative 3, because this is really that minus is like multiplying by negative 1, leaves us with x plus 3. Negative 1 times positive 2i minus 2i. And let's do it the same for the other one. So here you do the negative 1 times negative 3 again. And then negative 1 times negative 2i gets us plus 2i. So that does look a little bit different than how we're used to, because here that change of sign only happened to be different on the i's part. That plus 3 remained the same for both of those. So that's just something to keep in mind. So you very carefully set up that first. Then you're actually ready to start expanding this out. So we do x times x to get us x squared. I'm going to kind of keep track of the different types of terms on different lines since I'm going to have 6 of them. Then you do x times 3 to get plus 3x, x times 2i to get us plus 2ix, 3 times x to get us plus 3x again, 3 times 3 to get us plus 9, 3 times 2i to get us plus 6i. Then we have negative 2i times x to get us minus 2ix, negative 2i times 3 to get us minus 6i, and negative 2i times 2i to get us minus 4i squared. Notice how I wrote the minus 4i squared on the same line as the 9, because I know that will eventually turn into a constant. Now I can visualize this simplification a little bit better because I can notice that 2ix minus 2ix makes 0 and 6i minus 6i also makes 0. So I'm left with x squared plus 6x, and then for this remaining term, if I have 9 minus 4i squared, that's 9, let's actually write that on the same line. 9 minus 4i squared. I know that I squared, by definition, is doing the square root of -1 squared. Squaring a square root undoes each other. -4 times -1 gets us +4, plus 9 gets us 13. So x squared plus 6x plus 13 is our factor. Now we're ready to actually do our long division with that. So since I know x squared plus 6x plus 13 is a factor, I can do x cubed plus 5x squared plus 7x minus 13 divided by x squared plus 6x plus 13. So I want to ask myself first, x squared times what gets us x cubed? That would just be x. Then I want to do the multiplication off to the side. X times x squared gets us x cubed. X times 6x gets plus 6x squared. X times 13 gets us plus 13x. And then I want to subtract the whole thing. So that becomes minus x cubed minus 6x squared minus 13x. X cubed minus x cubed makes 0. 5x squared minus 6x squared gets us negative x squared. 7x minus 13x gets us negative 6x, and then you can drop down the 13. Thankfully, you should already notice that this is starting to work because x squared times what gets us negative x squared minus 1. And then when you multiply these guys by -1, then subtract that, that becomes just adding it straight down. Because if you think about it, you're basically doing minus multiplying by negative of this whole thing. And as soon as you do a negative times a negative, it becomes positive again. Negative x squared plus x squared makes 0. Negative 6x plus 6x makes 0. Negative 13 plus 13 makes 0. So in total, I just figured out that this guy factors into x squared plus 6x plus 13 and x minus 1. So I know that one of the zeros here I'm going to give you guys 2 pages to do this yourself. On yours. The next example was going to be identical to this one. It's going to be the same sort of process. So let's pause for a second because this is a meaty problem just to figure out what we've figured out so far. If you are given one complex zero, you can figure out the other complex zero by writing its conjugate. You can figure out one of the factors by first carefully doing 2 parentheses of x minus 1 version of the complex number, x minus his conjugate. First distribute that minusing, then carefully distribute all 6 of these terms, or all 9 of these terms actually I should say, because you have 3 terms that have to be systematically multiplied by another 3 terms. If you did it right, every term with an I should go away except for a single I squared, and that single I squared should be able to simplify because you know that the square root of -1 is -1. Then you want to take the original and divide him by what you just found. And in this case, what we just figured out was that if I have x cubed plus 5x squared plus 7x minus 13, he factors into x squared plus 6x plus 13 times x minus 1. And my goal is to find all the zeros. And now I have it down to linear and quadratic things. So I know from my linear factor, x minus 1 is 0, means x equals 1 is a 0. I know from my quadratic factor, well, I could re-find all the zeros by doing quadratic formula, or I could have already just known the zeros by how the problem was originally set up. So that would be -3 plus 2i and -3 minus 2i. Those would be our two complex factors. So all my total factors are 1, -3 plus 2i, and -3 minus 2i would be all three of our factors. Now, as you noticed, the messiest part of this was certainly having to expand out all of these complex numbers. So a lot of times, at least in particular for in-person exams, we usually try to give you, instead of a complex factor like -3 plus 2i, it might just be something like 2i. But being able to do this process will allow you to more easily do that on the real exam. And for online exams, it is randomized, so it's possible you might still get a problem similar to this. My video has become very long, but I think that it's actually worth the extra practice to see the rest of them. So I'm going to do one more example that's just like this. If you feel like you're already pretty confident with this process, don't feel the need to watch the next example. But if you feel like, I could use this example just one more time, I'm going to go ahead and go over this next example with you. So this is a very, very similar problem, but this time they gave you 1 plus 3i was the zero. So first of all, you want to list both of your complex zeros, because if 1 plus 3i is a 0, what else has to be a 0? 1 minus 3i. So now I need to figure out what I'm able to divide by. So I need to expand this out to get something with entirely real coefficients, because trying to divide by him without real coefficients is not going to be a very good time. First thing I want to do is distribute this -1. So I get x minus 1 minus 3i. Then I want to distribute the other -1. That should be an x, not 1. So we get x minus 1 plus 3i. Now I want to fully expand this out. If I really want to organize my work, if I noticed before I had terms that were x squareds, x's, ix's, i's, and constants. So maybe I just want to even note that to myself. So I've got to have x squareds, x, ix, I, and numbers. And let's just sort of keep track of what all those are as we're distributing. So I get x times x gets me an x squared. X times -1 gets me minus x. Oh, and then we've got more of those. X times 3i gets me plus 3ix. Then we have -1 times x gets me another -x. -1 times -1 gets me positive 1. -1 times 3i gets me -3ix. For the last set of terms, we have -3i times x. Oh, wait. I just made a mistake because I was moving way too fast. What's -1 times 3i? That would just be minus 3i. Now we're getting to 3i times x gets me, -3i times x gets me -3ix. -3i times -1 gets me plus 3i. -3i times 3i gets me minus 9i squared. And I noticed that under the numbers term because I know he will eventually simplify to a number. Now to start simplifying this, -x plus another -x gets me -2x. X squared just gets me x squared. 3ix minus 3ix makes 0. -3i plus 3i also makes 0. -1 minus 9i squared, or positive 1 minus 9i squared, I should say, is 1 minus 9. I squared, hopefully by now I've noticed it just becomes -1, but I could note the actual definition that I is the square root of -1. Squaring the square root makes -1. -9 times -1 gets us positive 9, so that is 10. So in total, I have x squared minus 2x plus 10 as my factor. Now I want to divide this by exactly what I just found. My original polynomial was x cubed minus 5x plus 16x minus 30. Now I want to actually start doing this division. So I ask myself, x squared goes into x cubed. How many times? Well, x cubed divided by x squared is just x. So I do x times x squared minus 2x plus 10. X times x squared gets us x cubed. X times negative 2x gets us minus 2x squared. X times 10 gets us plus 10x. And then I want to subtract the results. So that's a minus x cubed plus 2x squared minus 10x. And that's exactly what I write underneath. X cubed minus x cubed makes 0. Negative 5x squared plus 2x squared gets us negative 3x squared. 16x minus 10x gets us plus 6x. Drop down the negative 30. Then I want to keep on going. X squared times what will give me negative 3x squared? Negative 3. And then I want to make sure that it's actually working, so I'm going to multiply this guy by negative 3. Negative 3 times x gets us negative 3x. Negative 3 times negative 2x gets us plus 6x. Sorry, that was negative 3x squared plus 6x. Negative 3 times 10 gets us minus 30. And then we want to subtract the results. So minus and negative becomes adding a positive 3x squared, minusing a 6x, adding a 30. So 3x squared minus 6x plus 30, when we add that straight down, does indeed make 0 with each and every term. We're good. And if x minus 3 is one of our factors, if this guy factors into x squared minus 2x plus 10 times x minus 3, the 0 associated with x minus 3 is 3. And now I've found all the zeros of my polynomial. If I redid the quadratic formula with that result, x squared minus 2x plus 10, I would find my two other zeros are 1 plus 3i and 1 minus 3i. This is a very meaty chapter, so please make sure to take a look at your textbook for even more examples, and do be sure to reach out to your professor if you want some more examples as well.